impulse momentum theorem for rotation. Okay, remember we had an impulse momentum theorem for linear stuff, didn't we? What did we say? We said impulse is equal to delta P, which is what? P final minus P initial. So in other words, P final was equal to P initial plus some impulse, correct? That's for linear. Now, let's actually look at what we're talking about for angular impulse. This is linear impulse. So for rotation, what we're looking at is we have some sort of what?
Torque.
Yeah, we have some sort of torque. What we know is angular impulse is equal to J theta, okay? That is change in torque over time, okay? That is equal to change in angular momentum. Just like J is equal to change in linear momentum for a linear impulse, it is equal to, its rotational analog is equal to the change in angular momentum. So what we're talking about here, change in angular momentum, is it says the torque over time. Notice that is torque and then T. Be careful. Is equal to delta L, which is what? I omega final minus I omega initial. What that means is that we have to have some sort of a torque impulse to have a change in angular momentum. Why is this important? No change in torque, no torquing force, no change in momentum, angular momentum. So if the sum of the net torques is 0, then the change in angular momentum is 0. That's really what this means. It means if net torque is 0, then this is 0, which means this is 0, which leads us to conservation of angular momentum, just like we had conservation of linear momentum. In other words, L initial equals L final if we have no outside influencing torque being applied over time. I want you to think about what that really means in an actual thing. Look, I got this guy right here. This is got angular momentum. It's moving. It's going to continue to move unless I apply some sort of a torque. Oh, hey, I'm going to spin it a little harder. Oh, look, the angular momentum changed. It's not going to continue to change unless I spin it a little more. Or slow it down a little. Spin it the other direction. I'm having to apply a force perpendicularly over time. Over time means I can either do it very shortly or I can make it a longer time for a bigger impulse. Get it? Does that physically make you understand what we're talking about when we talk about this concept? Good. Because this stuff is really getting, as you notice towards the end of this class, the stuff is really getting sort of conceptually weirdly out there to a certain extent. All right, applying the impulse momentum theorem for momentum. This one's the weirdest one, and there's always one of these somewhere on the test. You have a 3 kilogram particle moving parallel to the x-axis along a line y, okay? And then we have with a velocity of 2 meters per second, what's the angular momentum of the particle when it's 4 meters to the left of the origin? So we have a particle moving this way, parallel to the x-axis, right? So here's the y-axis, here's the x-axis, okay? This thing is literally 2 meters away from the x-axis. What's the angular momentum when it is 4 meters to the left of the origin? Okay. Now, how do I know it's 2 meters from there? Because it says y is 2 meters along the line, y equals 2 meters. That's 2 meters this way. Guys, I need you to understand something. Do you see this when it is 4 meters to the left? That doesn't matter. The angular momentum for that particle is exactly the same along every part of this line that is parallel to this guy from the origin. If we're talking about what's the angular momentum about the origin, it doesn't matter. The angular momentum here, 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 it's all the same. Because think about what angular momentum is. We know angular momentum L equals what? mv r. R is perpendicular. It is on the line perpendicular to that guy, isn't it? So, yeah. So even if we stretch it this way and say, well, this is 4 meters, it doesn't matter because we just need the perpendicular component. The perpendicular component is still going to be the 2 meters, isn't it? So when we do this guy, we just say, okay, this is 3 kilograms, moving at a velocity of 2 meters. Our perpendicular is 2. So this ends up being 12, and the units are, go figure, kilogram, meters per second times meters. So this is 12 kilogram meters squared per second. That is the units for angular momentum. And you get tipper type style questions like this where it'll ask you, what's the angular momentum when it's, and they'll give you a series of particles about the origin. They'll say, okay, here's the point right here. I want to know, here's this point here, here's a mass up here, there's another mass here, there's another one way over here. Which one has the most angular momentum about that point? Well, when the one with the most angular momentum is the one that is perpendicularly furthest away.
And
So,
it's always kilogram meter squared per second.
yeah. So this right here, if you look at it, that guy that I just circled has the most angular momentum about that x. This one has, these two are the same. These two are equal, aren't they? Because they're the same perpendicular distance, and this one is the smallest because it is the closest to the, on the line perpendicular, that parallel to that point, that is the closest to that point. Okay? So now, let's look at angular speed of a flywheel. Having a rotational inertia. Here we go. Now we get to use the other formula. Flywheel having a rotational inertia of 0.15 kilogram meter squared. This should tell you a little bit about what's going on. If we have a rotational inertia, we got kilogram meters per or meter squared. All we have to do is divide by a what? A time. And then we have, all of a sudden, we have angular momentum, don't we? Okay. Now, what do we know? That's why you have to have it be torque times time. Because if you do I omega is, what's I? Kilogram meters squared. And then omega is radians per second. So you do actually get kilogram meters squared per second, which works. Okay, so what's the magnitude of the average torque acting on the flywheel about during this particular period? Okay, so we know that we are affecting a what? Change in impulse, aren't we? Or impulse, actually, not change in impulse. We're doing an impulse. Impulse is change in angular momentum. We know this is torque times time, and this is I omega final minus I omega initial, correct? So the torque is simply going to be this stuff, divide by T, divide all of this by T, right? Torque is that. So let's plug in some information here. We know this is 0.15. And really all we have to do is omega final minus omega initial, right? I comes out of both of them. Omega final is 4 minus omega initial is, decreases from 20 to 4. So this is 20. 4 minus 20. Divided by 1.5. So the torque is going to be negative because it is making it what? It's making it slow down, isn't it? So if it's going in one direction then, and it's slowing down, it means the torque must be being applied in the opposite direction, correct? It really makes sense if you think about it. Yep. Negative 1.6, and the units would be what for torque over, it's really torque times time, right? I omega is what? Guys, this is torque, so this is Newton meters. Right?
Per second.
Nope, just Newton meters.
Yeah.
Think about torque is what? FD? Or FR, if you want to think about it, FR. It's Newton meters. There's so many different variations to this, aren't there? All right, so conservation of momentum. We already said, suppose two discs are spinning on an axle together. They slide together, they collide and exert impulses on each other, don't they? If you've got one spinning and another one spinning and one falls onto the other one spinning, they are exerting an impulse on each other. Now, third law says what one applies to one, A applies to B, B applies to A. So what we have is the torque of A on B has to be equal to the torque of B on A, doesn't it?
What is A on B? Like, is that A minus B?
No. If you've got a disc spinning and you drop another disc onto it that's also spinning, when they touch, what's going to happen?
They're gonna grind against each other.
They're either going to speed up or slow down, aren't they?
Yeah. Oh, if they're going opposite ways, they'll slow down.
If they're going opposite ways, they'll slow down. If they're not going opposite ways, they might speed up. But whatever they're going to do, they're both going to do it.
Yeah, they're gonna match.
Yeah.
Okay. Okay, that makes
Okay. So, this is just action-reaction. This is Newton's third law. For every action, there's an equal and opposite reaction. Okay? Since all of the torques are internal, no external torque acted, did it? Okay? Then the momentum must be constant. No external torques means the initial angular momentum equals the final angular momentum. We just talked about this, didn't we? And this is where we say L initial equals L final. It's really what it means. This right here is Newton's second law. Oh Lord, now what? Turn this off and put it over here. Okay? It's really kind of Newton's second law, isn't it? Sum of the torques times time is equal to the change in angular momentum. Okay, so internal interactions in the system, this is the important part right here. Internal interactions of the system cannot change the total angular momentum of the system. It has to be an external torque acting over time. Okay? Something external has to interfere. Just like with if something is moving along and is rolling along, unless you apply an external force to it, it's not going to change what it's doing, the direction or how it's going. And a good example of this is skaters move faster when pulling their arms, as this decreases their moment of inertia, allowing their angular speed to increase. I want you to think about that. We've just done this earlier. We know that L equals I omega. Therefore, if I sit on this stool, and I'm going to with these weights, and I'm going to rotate, then what happens?
Speed up. Slow down.
If I'm rotating, if I start the rotating with them out, nothing's going to change unless I decreased my inertia, didn't I? So what happened to my angular momentum? Or my angular momentum's the same. What happened to my angular velocity? Oh boy, I need it to decrease. I don't do spinning well. So I increased my inertia now. So my angular speed went down, didn't it? Okay? Feel free to try that for yourself. It's interesting. Okay? So.
Are you using the wheel in another class?
No.
Oh.
I'll be using it next, but yeah. All right. So let's look at this. We pull our arms in to go fast, spin faster, and push them back out to spin slower. Okay? All right, so circular disc platform rotates about a central axis. The platform has a mass m, radius r. In other words, merry-go-round. Student mass m/4, so it's a quarter of the mass of the merry-go-round, walks slowly from the rim towards the center. So what's going to happen? If you start pushing and the kid's on the outside, and then the kid decides to move to the inside, what's going to happen to the speed of the merry-go-round as the kid walks towards the center? It's going to speed up. It should increase, shouldn't it?
Would slow down.
So here we go. This is how it works. L initial equals L final, right? Well, what is L initial? I omega initial, isn't it? Well, this has got to be the I of the merry-go-round plus the I of the person, doesn't it? So what's the I of the merry-go-round? The I of the disc is going to be, so it'll be I disc plus I student times omega initial equals what? I disc plus I student times omega final. So let's figure out what that is. I of the disc is going to be 1/2 mr squared. That is not going to change for either of them, is it? What's going to change is the inertia of the student, because where they're located is going to change, isn't it? This is going to be m/4 r squared times omega initial. And then this is now not going to be, this is still going to be m/4, but instead of r, it is now r/2 squared times omega final. Okay? And really we shouldn't say omega initial because it gave us in the problem, it gave us what? Omega? So let's just call this omega. All right, so let's see what we end up with omega final. Well, 1/2 plus 1/4 is what? 3/4. So this is 3/4 mr squared omega. And now we have 1/2 plus 1/16. So it'd be 8/16 plus 1/16 is 9/16. So this becomes 9/16 mr squared omega final. Well, the m and the r squareds go away. Multiply by 16, divide by 9. 16 over 9, that's going to go away. So omega final. This becomes 4, this becomes 3. Oh, hey, look at that. 4/3, the original angular velocity. Which is what we expected it to do. This is that part of the problem where you stop and you look and you ask yourself ahead of time, what do I think it's going to do? Okay, and you look at your final answer and go, oh, hey, look. I was right. It should speed up.
No, but the whole system speeds up. But with the kid, he's slowing down.
Well, he's sitting on the disk that's rotating. The whole system is the...
The rotational speed will increase with changing the speed.
Yeah, may or may not. Okay. Bullet of mass M is shot at speed v into a block of mass m. The bullet hits a distance r from the center of the block as shown. Uh-oh. This is our... What's going to happen to the block? The block flies into the air while spinning. If you thump a block and it's not at the center, what does it do? It turns, doesn't it? Yeah, exactly. Calculate the angular speed of the block. So this becomes a much harder question. But it doesn't if you know it's going to have to conserve what? Angular momentum. L initial equals L final. The initial momentum is of just the bullet, which is mvr. It does actually have angular momentum, doesn't it? Because it's going to pass by the center line of the block, right? This is the block. Here's my R. So yeah, it's off the center line, so it has angular momentum with it. That's the initial. In the end, it's now going to be what? In the block, spinning. So we have I of the block plus I of the bullet times omega, because it asks for the angular speed. So we can mix and match these as we need to fit the situation. If nothing's spinning, then it's got to be MVR. If something's spinning, it's got to be I omega. Okay, so now we just plug in. What is I of the block? Well, for a rectangular block, let me give you a hint. It's 1/12 mr squared. But that would be the length of the block, okay? So this is going to be, and they would normally, in an AP question, they would have given you the inertia. They're not going to expect you to remember that. So this is 1/12 mass of the block, and this is 2r, 1/12. 2r squared, because that's the length, right? Plus the bullet, which would just be like a point mass, wouldn't it? Mr squared, except r, little r. Little r.
It's little m.
Oh yeah, little m too, thank you. Be careful with this. Little m, little r squared times omega. Alrighty, so let's figure out what we got here. We've got not enough room to work, but I'll come up here. MVR, that's little m by the way. 2r squared would be 4r squared over 12, so this would be big M r squared over 3 plus little m r squared, and this is all times omega. I'm just going to multiply through by 3. 3 little m v r equals big M r squared plus little m r squared. You can get rid of an r at least, can't you? So now omega is going to be equal to,
But how could you get rid of that 3? You have to multiply the little m r squared by 3 too.
yes, that should be a 3. I'm being sloppy. It's late in the day. If it weren't for Sam, what would I do? M r squared plus 3 little m r
It'd be 5 minutes.
squared. It'd be what?
It'd be 5 minutes, but then Addie would listen.
Yes.
No less. 2 minutes.
Yeah. All right, so now we just have to divide, right? So 3 mv, I'm going to get rid of this r and the squareds. Those go away. So this will be 3mv divided by big M r plus 3 mr. And that would be that. How would the maximum height reached by the block compare if the bullet was shot directly into the
It'd be a lot more.
center
Well, it wouldn't be a lot.
of the block? If it's pushed into the center, what would happen?
Then there's no spinning.
No spinning.
So that means more energy goes into moving it. Yeah. Linear vertically than spinning it.
We have to work that out. Just do it just right.
I don't know. Let's look. This is what we think is going to happen, isn't it? Yes?
But then also
Let's look.
less initial.
Well, yeah. Less initial kinetic energy, too.
Just
Because there's no angular momentum to begin with, is there?
right.
Okay, so what we're dealing with is this. Instead, so this is the big question. So what we really have is P initial equals P final, right? So little mv equals big M plus little m times V final. So V final equals little mv divided by big M plus little m. Wow. Okay. So, I don't know. Let's look. What do we know about angular speed versus linear speed? So this is center, right? What's off center? What do we know about off center? What do we know about omega? Omega equals what? V over V times R, right? Okay. So we really have V times R equals 3mv over mr plus 3mr. Yes?
You can get rid of R's.
You sure? It's V over R, not VR. It's V over R.
Yeah. My bad. Yeah.
So you can get rid of the R's, can't you? Okay. So let's compare. So now we have V equals 3mv over what? Big M plus 3 little m. This would be V final. V final. So which one's going to be bigger? Is there going to be any difference?
Off center will be slightly larger.
But then that's just. Huh.
Here's the thing. Where you have angular momentum is conserved. Where you have linear momentum is conserved. They're two completely different things. You have to separate them. They're conserved separately. So is the linear momentum still going to be conserved in the off-center one? Yes, it will. Believe it or not, the linear momentum is still conserved. We would have to do this as two separate problems. How high would it go, or how far would it go versus how much it rotates, right? It's weird, but the extra velocity, final velocity we have here is what? That comes to the rotation.
So the rotation will make it.
Here's the problem though. If linear momentum is conserved separately from angular momentum, doesn't that mean no matter where you hit it, it's still going to be this at the end?
Because linear momentum doesn't matter where you hit it.
Yeah, linear momentum doesn't matter where you hit it. So the linear momentum is still going to be conserved, which means what? Even though the block is going to spin in the second case rather than the first case, part of the V that you're getting that seems to be the higher speed is still just the rotational part of it, and that doesn't play into how far up it goes. It just plays into actually getting it rotated around. Does that make sense to you? So guess what?
That V is really the tangential velocity.
Yes,
isn't it?
it's really the tangential velocity, not the linear velocity. So this is tangential, not linear. So the reality is right here. Yes?
Sam McAbee is checking out.
Okay. So the reality is they both the heights are the same. Okay? All right. So the height of both of them is the same. Strange, isn't it? All right,
I mean,
so.
thinking about it, like something
guess the kinetic energy of rotation.
Yeah.
Not related to
Yep.
I wish we could test.
translation.
I wish we could test it like.
Well.
I don't know if I have that sheet.
5-6 static equilibrium. I thought I gave it to you guys at the same time I gave you 5-5. Did I not?
It's the same in the package.
Oh, it is.
I thought I gave it to you.
Because she gave us this small one. The upside down weird packet was just
Yeah.
the little list.
I gave it to you.
And then she gave us the new packet, bigger one, and it has all of us. It has both.
Yeah. I think I gave you both of them. Static equilibrium you're going to have an easy time with. It's not that big a deal. Basically, just what it says is, what do I need to do and where do I need to put weights to make sure no rotation actually happens? That's really what static equilibrium means. There's a translational and a rotational component. So, yeah. See you Wednesday. All right, so here we go. Conditions for equilibrium. If you want static equilibrium, and that's what we're talking about, static meaning doesn't move. Okay? Now, we now have to consider two different things. Up to this point, equilibrium meant that there was zero net force, which means you were either at a constant motion or you were at what? Stop, right? Now we have to consider both linear or translational equilibrium, which is the sum of forces is zero. That's this guy right here. And then we also have to, though, consider rotational equilibrium, which is that the sum of the torques is zero. So we really have to consider both of those things, all right, in static equilibrium. It's not a hard set of things to do. You just have to make sure you look at both of those. And most of these problems have to do with both of either one or both of them, all right? So we've got a guy sitting on two scales. 170 centimeter tall person lies on a light, massless board, nearly impossible, but we'll go with it, supported by two scales, one under his feet and one under his head. The two scales read 31.6 kilograms and 35.1 kilograms. Where's the center of gravity for this person?
So
Is it further to the right or further to the left? It's heavier to the left, isn't it?
skills. Oh, on the picture. Yeah.
Okay.
Picture. Yes.
So basically what we have to think of is this. Where is the person's center of gravity going to be? Okay? So what we have to do is we have to picture this guy as having, probably we think because this guy is bigger than this guy, that this is the pivot, right? From the standpoint of rotational equilibrium, that would be the pivot, wouldn't it?
Yeah.
Okay, so we've got a torquing force this way and a torquing force this way, don't we? We know his translational is zero. Sum of forces is equal to zero. How do I know that? He's what? He's laying still. So obviously nothing's happening. Nothing's being done. He's sitting there, so we know that. Now what we need to know is what is the sum of the torques. We're pretty sure he's not rotating, so we know the sum of the torques about a pivot, about some point P. We'll call this pivot point P, right? Or you can think of it as, there's my pivot point. All right, so that sum of the torques around the pivot is zero because clearly he's not rotating either, is he? All right, we know he's 170 centimeters tall. We don't know exactly where his pivot is. We just know it is 170 centimeters from here to here, or 1.7 meters, correct? So we're going to call this x, which makes this 1.7 minus x, all right? That typical algebra cheat that you use in setting these types of problems up. We have to do that because why? Yep, and in reality, we also have a third mass if this is his center of mass, we also have mg right here too, don't we? His mg? Okay. But that's at the pivot, so guess what? We don't care, do we? So this is going to be everything pointed down versus everything pointed up. Now, what we have to consider is if he's laying on these, his whole mass is down, which means that this is a reactive force here and here, correct? Which means we don't want to draw these downward right there, because if what we're reading is upwards, that's what we've got. Normal force pressing up. Remember, weight on the scale is normal force, correct? So we have normal force 1, we have normal force 2, and then we have mg pointing downward. Each one of those is going to happen. So really what we need to look at is what do we want up, positive, and what do we want negative? What's going to cause a clockwise rotation about the pivot? What's going to cause a counterclockwise rotation about the pivot? So the first thing we need to do is mg times 0, right? That's at the pivot. Which one's going to cause a counterclockwise rotation about the pivot? Yeah, F2, right? So F normal 2 times, and this is, we said this was what, 1.7 minus x? And this was x? So this is minus x. And then minus Fn sub 1 times x. Okay? Because Fn sub 1, if it's the greater one, it would make him rotate clockwise, wouldn't it? Do you agree? Yeah. So this guy would make him rotate this way. This guy would make him rotate counterclockwise. This is clockwise, so that one is a positive. Clockwise is negative, so that makes this negative, and that makes this one positive. And this one's at the pivot, so it's a zeroed out. So that one goes away. So now we actually plug in. Think about it. 35.1, actually this one is what, 31.6? So 31.6 times 1.7 minus x, this is equal to 0, minus 35.1 times x. So now all we have to do is figure out what x is. $31.6 times what, 1.7? $53.72 minus 31.6x minus 35.1x. Okay. 31.6 plus 35.1 is 66.7. Bring it to the other side. We get 66.7x equals 53.72. Divide. And we get, I get 0.81 meters, right? So 0.81 meters from his head, right? That's where his center of gravity is. All right, now we have the typical Yogi Bear scenario. You probably didn't watch that when you were little. Yogi Bear likes his picnic baskets, right? His picnic basket. Hungry Bear, weighing 600 newtons, walks out on a beam in an attempt to retrieve a picnic basket hanging at the end of the beam. The beam is uniform, weighs 200 newtons. You know why it says it's uniform? so we know where the center of gravity is for it, right? Center of mass is, it's right in the middle. So immediately what we know is right in the middle of this beam, we have, what, 200 newtons? Correct? At the very end of the beam is a picnic basket that weighs, so we got 80 newtons going downward this way. Maximum tension the force a wire can stand is 700 newtons. And we've got this bear at 600 newtons. So the bear is right here at 600 newtons downwards. So we got a lot going on, and the pivot is right here. This is my pivot P. Now, here's the problem though. We've got another thing happening, another force happening here. This force is force T, isn't it? This is the tension on the rope. But we don't want that part of the tension. We want what? We want the upward version of that tension. So if this is theta, correct?
Yes.
Which means this is T sine theta. So let's figure out where all of this is. Where all these beam things are. How long is the beam? The beam is 6 meters long, right? So we know that this is 3 meters. Do you agree? Okay. The bear, we don't know where he's at. So he is X. And then all the way out to the end where the picnic basket is 6 meters. So now we know where all these forces are. So the sum of the forces, sum of the torques from the pivot is equal to 0, correct? So now let's start with the bear. The bear is going to cause it to go what? Yep. Clockwise, clockwise, and clockwise. So this is going to be negative 600 times x. Do you agree?
Yep.
The beam is also going to cause it to go clockwise, isn't it? So minus 200 times 3. The picnic basket will also cause it to go clockwise if we let go of that string, correct? So 80 times 6, and then we have that one thing that's going positive.
The T sine theta.
T sine theta. So that would be 700 sine of what? What did we say that angle was? Oh, angle is 60 degrees, so sine 60.
Oh,
So where is the bear? How far can the bear walk out to the beam before that breaks? See, here's the thing. He can only walk so far and he's at equilibrium. If he walks further than that, what happens? He pushes the force too big, that collective torque too big, isn't it? And the rope snaps. And in other words, the downward stuff is bigger than the upward torque, isn't it? So let's figure out where he's at. Well, we did. 700 sine 60 is positive. That is the upward, isn't it?
Yeah, it is.
So we get 600x on this side, and we just sum up the rest of them. So we have negative 600 minus 480 plus what? 700 sine 60?
Yeah.
That's what, 350? Oh, 606? Plus 606.2. So I'm going to take that 606, subtract 600 from it, subtract 480 from it. Oh, wait a minute. Hey, did we forget the times 6? I forgot the times 6 here. This is times 6, isn't it? We got to do the times 6. Because that's the distance.
6 meters from the.
Yeah. So we do what? 700. Let's start this over again. 700 sine 60 times 6 minus 600 minus 480. And then we're going to divide by 600. So we get 4.26 meters out onto this from the left. So actually he can move past the center, can't he?
Wow, that's kind of surprising.
Does surprise me too. So it tells you if his reach is long enough, he might actually be able to get to the picnic basket. That's right. Oh, hey, did I give you this and there wasn't any? Wow. I don't think I meant to do that, but that's okay. So, yeah. No, I don't mind at all. That's unfortunate. I did not realize I had not. We'll talk about them. Sure enough, I'm going to pause it for now. There we go. Back to recording. Okay, so we've got a strut and a beam. Okay? We've got a strut on a hinge, and we've got a cord tying it up. Okay? Hanging from the end of that strut. It says calculate the tension in the string. The string is at a 30-degree angle to the ground. You can see that you've got a 225 kilogram mass concrete block hanging from it, and the strut is 45 kilograms. The big thing that you're going to start seeing in these type of problems is now it's getting more real world. It's no longer a massless strut and we're just hanging stuff off of it. It has mass. It will do things. Our pivot is right here. This is the pivot or the hinge. That's super important in these problems, okay? We got to know what's going on. Now, calculate the tension in the string. Well, all right. So what we have to figure out is what's going on here. We know the strut is uniform, right? Uniform strut, which means that its mass is, center of mass is at the center, and it's down here, isn't it? mg. And then we've got this guy coming down at mg as well, don't we?
Is that at the end?
Yeah, that is at the end of the strut, hanging from the end.
Yep.
So you always kind of got to think about that and look at it. So the first thing we're going to do is we're going to look at, okay, and then we have this tension going this way at this end, but we don't want that. We want it to be, what? We want this chunk of it, yes? Okay, and here's the thing. Actually, I'm going to put this in a different color because on all three of them, we're kind of up a creek because for all three of them, we need this component of this guy, we need this component of this guy, and this component of that guy. Because they have to be the component perpendicular to the strut, don't they? If they're a torque, we want the one perpendicular to it.
What about the picture? Look at, oh, weird 45 perspective.
Well, we do know it's 45 degrees because this said it was 45 degrees.
Oh, well, yeah.
That's taken into consideration here. So if we look at those, let's look at this picture. So let's look. We set up the sum of the torques at the hinge. That's equal to 0 because it is in equilibrium. We've got the beam. It's going to go clockwise, right? And I always classify these. This is clockwise. This is going to make it go clockwise. This is going to make it go counterclockwise. If I go ahead and write that out, then I make sure I get my signs correct. Okay? So everything clockwise is negative. So that's the weight of the beam. So that's this right here. So this guy, weight of the beam, headed down. That's going to be sine of 45 degrees, isn't it?
Clockwise.
Clockwise is negative. Counterclockwise is positive. So we've got negative W of the beam, sine of 45. And this length, we know it's L, because it doesn't give us the length, does it? So this thing is L, so this is L over 2 because it's in the center. L over 2. Now we've got the block, which is the weight of the block, which is mg for the block. Again, sine of 45 degrees, right?
That's like an in, so it's L.
Yep, that's just L. And then we have this string. Now, where did the sine of 15 degrees come from? All right, look. This is 30 degrees, isn't it?
Oh, 30 plus something.
Well, this is 45. So what you got to do is you got to do some math in here. If this is 45 degrees, this is what?
180.
180.
So
So this would be 135. So if that's 135 degrees and that's 30 degrees, that's 165, which leaves a grand total of 15 degrees. Okay. So we've got the y version of that this way. This is the same thing. That's still sine 15, right? Okay. So that's sine 15. All right.
triangle is for 180.
Yep. So t sine 15. And we know all that has to end up. So we start plugging stuff in. 45 kilograms times 10 sine 45 times 1/2, right? Now, do you understand why it's 1/2? How did I get rid of the L? I just divided through by L. It's equal to 0 on the other side, isn't it? So if I divide all of these through by L, this is still divided through by L, which is still makes it 0, doesn't it? So it's one.
One L over 2, now it's just 1.
Yeah. So we have 1 over 2. So we plug all our numbers in and we get a grand total of tension of 6,761 newtons. That's how much tension is on that wire or whatever. Okay? The string. Now, it says find the force the hinge exerts on the strut. So we want to know how much force is right here. The hinge exerts on this strut. Okie dokie. So how do we do that? It's still in equilibrium. It's still not moving, is it? So we have a force being exerted on this hinge this direction, and we have a force being exerted on the hinge this direction. Does that make sense? We're calling them H sub x and H sub y. Okay? So in the x direction, we know it's not moving, so the sum of the forces in the x direction is still 0. Well, what's acting on that? The only forces we have acting on that hinge come from what? The only things actually touching it that are pulling on it, yeah, in the x direction are the wire, right? The tension and the ground. Look, the wire from the block doesn't do anything. Well, no, because here's the thing. All of the force of it is either what? This way or that way. Neither of those is in the x or y direction. This is straight down in the y direction, isn't it?
Yeah.
It does not affect the x direction. We'll see it come in the y direction.
Oh. Okay, so it doesn't.
Yeah. Doesn't do anything. Same thing with this guy. Also, only in the y direction. So the only things that have an x component are the pivot, the wire, this wire right here, and the ground. Whatever force is on the pin itself,
Okay.
where it touches the ground, the hinge, where the strut on the ground, right, that end, and the wire on the other end, okay? And I got a lot of stuff going on here, so I'm going to erase all that temporarily so we can actually see what we're doing. All right. So right now we have this, and then we have the X component of this, don't we? Which, if you think about it, if this is 30 degrees, then this is also 30 degrees, isn't it? Along the wire. So that's why it is T cosine 30. So this chunk would be literally T cosine 30 degrees. Okay? But I want to make sure you understand that I've got it pointing in the wrong direction. It is actually pointing this direction, isn't it? Because T goes back this direction, right? So this is positive and this is negative. Thus, h of x minus T cosine 30 equals 0. So we can now actually, I mean, if it makes sense, the H component on that is only caused by the wire at the end, right? Think about it that way. So T cosine 30, we know what T is. We plug in. We know that H sub x is T cosine 30 degrees, which is 6761 cosine 30, right? Which is this, 5854.
Okay.
Now we got to figure out what's going on in the y direction. So let's erase it. So whatever's happening in the y direction, whatever this is pointing upwards, we have to take into consideration all the other pieces. This has a downward component, so it's negative. This has a downward component, so it's negative. And unfortunately, so does that tension, right? So the tension is going to be, it's got this way, tension is this way. So we need the downward chunk of it as well. Okay? So if the one was T sine, if it was T cosine for X, it's going to be T sine for Y, isn't it?
Yeah.
So this is T sine 30. This W of the block is what? 225 times 10? Well, 9.8 really. This for the beam, we said the beam was what? 45? So this is 45 times 10. We'll just use 10 for here. Okay. So now we just set it up. In other words, H sub y, the reactive force of H sub y, since this is all equal to 0, is really just all of these guys added up, isn't it? These three right here added up. So that's what it ends up being, which makes sense if you think about it. So 45 times 10 plus 225 times 10 plus 6761 times the sine of 30 degrees. Okay? And you get 6080, approximately. Now, if we know h of x and we know h of y, then by the Pythagorean theorem, we know what the total h is on that hinge pin. Remember? H sub x squared plus h sub y squared is going to be equal to the total h squared. So to find h, we simply take the square root of the squares of the sum, right? So that's what I did. Took this and squared it, took this and squared it, squared it, added them together, took the square root, and you get a total of 8,440 newtons of force on that hinge pin. Now, to solve these types of problems, notice what we're having to do. We're having to figure out what's perpendicular to whatever it is, right? What's perpendicular, where the hinge is, or the pivot is, how far away each one of them is from the pivot. Those are the biggies. And then we determine whether it's going to make it turn clockwise or counterclockwise. And then we set up these forces diagrams, okay? So now we got ladder resting against a smooth vertical wall. You know what that means? That means we've got contact here and then contact here with the ground. Mass of the ladder is m. Coefficient of static friction between the ladder and the ground is 0.4. Find the minimum angle at which the ladder does not slip. Now, if you've ever been on a ladder, you know this is true. You got to get it at a certain angle. If you get it past that, it starts to whew, out from underneath you and you go boom. And it's not fun. Yep. So here is your picture. We know the ladder is L long. We know the center of the ladder. Since it is a uniform ladder, this is mg for the ladder. And it's at L over 2. Notice how I've set the pivot at the ground, correct? So the pivot is at the ground. We've got a normal force acting with the ground, don't we? Normal force is acting upwards, correct? I don't like it there. I like it here. Normal force. We've got the weight of the ladder acting downwards. And we have what? Normal force with the wall. So the normal force with the wall, since it's touching, is pushing this way, isn't it? So the force with the floor, the force with the wall, the force of the ladder, and that's it. We've got 3 forces, one of which is at the pivot. Nope. So when we set up our sum of torques, since we put that lovely sum pivot at the floor, that means this guy doesn't matter to us in this case, does it? It's the 0. So we know if it's not slipping at 0 because it's not rotating, is it? When it begins to slip, it begins to rotate. Slides and rotates at the same time. So now, and we forgot about friction. It wants to slide this way, so it must have static friction going the opposite direction. Okay? We're going to stop here, and we'll finish this one next time, okay?